All right, so most of the basic problems I saw with this final standard that we assessed on Thursday came from just not remembering, I think, the definitions of image as TBIL defines it in kernel. So remember, image is also another way to say range. So we want to know what can we actually map to. Now, if we're thinking about what we can map to, we are looking at our code domain here. So right off the bat, I know that my image is a subspace of R3, and so is the basis is going to be vectors from R3. So this is really important because if I'm outside of that, if I try to write something with five, like a column vector with 5 elements, I am not talking about the image. Now, range, as we talked about, is really just saying, look, that set of, what do we call them? Linear transformations of our standard basis vectors. If we think about what those are, right? If we go back to that previous, I hope it was a previous one, right? This previous idea here of these transformations of our standard basis vectors, we realize that we're just talking about linear combinations. And so we're kind of talking about span, right? We're going back to that idea and basis, right? And for both span and basis, we're in this idea of like, we can write dependent vectors as part of our span. It's not a problem. It's just redundant information. So the laziest way to knock the image of T out, which by the way, image, remember, is a whole subspace. The laziest way to get this first part, and I saw some people do it and I just kind of smiled as I saw it, is that we could write down that our image of T is literally just the span of all of those little column vectors that we would have created. And so some folks did this. It was, like I said, lazy but clever. Negative, oops, we don't have a 1 in that last one. So 0, list the next one. So for x2, that would have been a vector of 1, negative 1, 1, 0. We'd have the x3, which is negative 1, negative 3, negative 5. And then we would have 4, 2, negative 6, negative 5, and the 5th, which is 0, 8, 10, right? So that would definitely do the same work, right? It's not particularly efficient, which is why you were asked then for a basis. So if we want to talk about our basis for this, or if we want to do this more cleverly, we realize that in order to have a basis, we don't want any of the dependent vectors. We want to kick those out. And that's when we're going to those pivots in our REF matrix to say, oh, right, we can look at this. We can see our V1 and our V2, these first 2 vectors in my span, they are, one is just a negative multiple, right? It's a scalar multiple by negative one of the other. So I can just pop one of these, pop one of these out, and I'm still getting the exact same space in my image, right? Because this one here is dependent. Now we see the same thing with our last 2 vectors. Those 2 vectors are linear combinations of other vectors we already have, so we can take these out as well. So if you wrote your span with just the 2 vectors that end up in our basis, right? Our basis is a set of vectors. Then we don't want to have the word span, we just want to list those 2 linearly independent vectors that if we did the span would give us our subspace. That's fine. Now again, since we're in talking about different ways I could have written that subspace for image, laziest, write all the freaking column vectors, say span. Less lazy and probably more efficient, write out your basis first and then just toss span on it, which is now what I have. Or you could use that sort of solution set language that we've been doing previously, right? Of like, oh, okay, well this is some a minus b, negative a minus 3b, and negative 5b for some a and b in the real numbers. Yeah, I could have written that too. And that's just coming back and rewriting that basis or that span as a linear combination, right? There's one more way, which is to write our little a times that first vector in our basis and b times that second vector in our basis, where a and b are within wheels, right? Everything here, these three up here at the top are all equivalent ways to write that subspace. I do think the span notation is the cleanest considering how we find our image typically, right, by using these pivot columns. But again, if we just think about image as range and we come back up and look at what we're talking about with R3, I think we won't make as many mistakes as I was seeing on the quizzes, because a lot of students had something with a 5 element vector, right? A 5 by 1 column vector, which is no bueno. All right, so let's look at the next question. Next question said, oops, now that we have that, I'm gonna move her back, but I don't know if I can. Now that I have that, yes, find me the kernel of T. Now the kernel is everything in the domain that maps, oops, to our 0 vector in our codomain. All right, now this means very, very different vibe, right? Instead of being in R3, we're in R5 now. This is the thing that's analogous to solving our homogeneous linear system, right? Because we want to know, when am I going to map to 0, 0, 0? Basically, we're setting each of these elements here equal to 0 and saying, how the heck could that happen? Which we know depends entirely on our free variables. Whoop, whoop, whoop. So while we used the pivot columns in our answer for A, we're going to use the non-pivot columns in our answer for B, because they're the things that tell us all of those spaces, ways that we could get back to the 0 vector, right? All those infinite number of ways that we could do that. Okay, so now we go, okay, well, simplest is to probably think of this as our homogeneous system of equations. Imagine that we have our augmented matrix here with zeros on the end after that line, and go, okay, well, let me write this, because that's just what my brain requires sometimes. Plus 3x5 minus 2x5. Now, I'm sure a lot of you didn't have to do this, but you know, some days you're just not feeling as smart as other days. And that is that day for me. Ugh, I don't like that I don't have a space. It's fine. I'll just shove her over. x3 plus x4 minus 2x5. And, oh yeah, we don't have anything else. This is it. So we can look at this, see our free variables exactly where we expected. x2 is free, x4, and x5. So we know that we have these 3 different free variables. We know that our space, which the kernel is, right? The kernel of T is an actual space, has to span, or has to not span, but has to be a subset of R5. So we need 5 elements. A row, column vector that's 5 by 1. And we can go ahead. The second element is free, the fourth element is free, and the fifth element is free. Let me fix that up. And then we can go ahead and rewrite the third and the first element, those pivot pieces, as the free variables we just defined. So here we'll have a 2c minus b, and here we'll have 2c minus 3. Ugh, I'm just really not using enough space, plus a. Right, so I'm just solving each of those out. So we have x1, and I've replaced all those things with a's, b's, and c's. Since we have a, b, c, oops, got excited, c in the real numbers. All right, so now we have our lovely kernel space. If we want the basis for that kernel space, we have to rip apart all those different column vectors that we would use linear combinations of to get to this kernel. So we have our set here. We have 1a, 1a, and then no more a's. Yes. We have oops, close off my vector, start another one. We have negative 3 b's, no b's, negative 1, 1 and 0. And then for c's, we have 2, 0, 0, oops, not 0, 2, 0, 1. And that is our basis, that set of vectors. Now the last question here said, okay, let's see if the rank nullity theorem holds here. So this was this idea that nullity is the dimension of our kernel and our, sorry, I like to have my things match. Rank is our dimension of our image of T, right? So we had these two things, and what we noticed is if kernel is determined by our non-pivot rows and our image is dependent on our pivot rows, our pivot, did I say rows before? Oh my God, non-pivot columns, pivot columns, then when we add these two dimensions back together, we should end up with the number of columns we originally had. And it's exactly what we see here. Our dimension, the number of column vectors in our basis for our image is 2. Our nullity, right? So our dimension of our kernel, there are 3 column vectors in our basis for our kernel. If I add those back together, I get 5, which we can think of either two ways. It's the number of columns in our standard matrix, or looking back, right, this is the dimension of our domain, our R5. So these will be the same no matter what. But cute. So this will always happen. It's a nice little check to make sure you didn't do anything wrong, especially once you find your basis, because if they don't match, then we're in trouble and something has to have gone wrong.